Students, we'll start with our today's lecture. So in the last lecture we had completed the topic space sharing. Today we'll be starting with gang scheduling. Now what is gang scheduling? For multi-processors. Now when we are talking about multiprocessors, the time and space sharing which is there is somewhere interconnected, and because of which there is elimination of context switching overhead, because of which an equal obvious drawback is time is wasted when a CPU blocks and remain idle until it becomes ready again. So before and after the process is being converted, there is some time which is being wasted, and because of which the CPU sets idle, means it has nothing to do, and that is the reason, while again when it is allotted some work, it has to start from the very first. As a result, algorithm that try to schedule in both time and space jointly. Now in space, that is in the space sharing, and in the time, the algorithm which communicates particularly for threads that create multiple threads. Threads that create multiple threads, which typically require to communicate with each other, attracted a great awareness. So here when they need to communicate with each other, they should be great aware that yes, we are communicating with multiple processes, that is multiple threads in one process, wherein multiple processes will be going on. If the threads of a process are independently scheduled, then problems arises. So if they are independently allotted to some process, then there will be a problem. If x0 and x1 are threads of a process x, and y0 y1 are threads of a process y, threads x0 and y0 are time shared on CPU 0, threads x1 and y1 are time shared on CPU 1. Threads x0 and x1 frequently need to communicate with each other. Communication sequence is that x0 sends message to x1 with the then sending the response to x0, followed by another such sequence common in client server situation. x0 and y1 initiate first. In time slice 0, x0 sends x1 a request, but x1 does not get it until it runs in time slice 1 starting at 100 milliseconds. It sends a reply without delay, but x0 does not receive the reply until it runs again in 200 milliseconds or microseconds. The net result is one request reply sequence every 200 microseconds. Performance is really affected. So what is being told here is, this is all the example they have given, that is there are two threads of x process, that is x0 and x1, and similarly there is two threads of process y, that is y1 and y0 and y1. So while they are communicating, what they will do, they will start threads x0 and y0, that is both the first threads of x and y will start on the time shared of CPU 0, whereas vice versa, threads x1 and y1 will time share on CPU 1. Threads x0 and x1 frequently need to communicate. Therefore, x0 and x1, that is CPU 0, need to communicate with each other. Similarly, y0 and y1 also need to communicate with each other frequently for the data processing. The communication sequence is that x0 sends a message to x1. Similarly, y0 sends a message to y1. So if x0 is sending a message to x1, then sending response back to x0 followed by another such sequence is a format of client server messaging. That is, client is asking for request, server is responding likewise. If now they have given second criteria, that if x0 and y1 initiate first, that is first CPU 0's first part thread and CPU 1's second thread, in time slicing means when time is divided, 0 comma x0 sends x1 a request. So 0 comma x0 will send a request, but x1 does not get it. x1 will not get that request until it runs in time slice 1 starting at 100 microseconds. So it will not get the response back, that is here somewhere, until and unless it runs at 100 microseconds. It sends reply without, now it got the request at 100, now it will send the reply when it turns 200 microseconds until it runs again to receive the reply. So x0 has to become 200 microseconds in the time slice so that it will get the reply. So here when this time sharing is done, in that spaces a lot of performance is affected because it takes a lot of time. So gang scheduling can solve this problem. Gang scheduling has three divisions. Complete unit of related threads are scheduled just like a gang. So complete unit, a bunch of threads is being scheduled like a gang. Every member of the gang run at once on different time shared CPUs. So all the whole gang at one single time run on different CPUs. Every member of gang starts and ends its time slice together. So with this, there will be no hustle and bustle over the processes. What will happen, they all together start at one single instance and they end up also at that single instance. So here and there time framing is not disturbed. All CPUs are scheduled synchronously. So here synchronously means in a process, that is in a sequence, gang scheduling works. So this process, gang scheduling, works like this only. So gang scheduling, as I explained you, groups of related threads are scheduled as a gang, that is a unit, and which is called a gang. All members of a gang run at once different time shared CPUs, and all gang members start and end their time slices together. So this is the three parts in which your gang scheduling is being defined. So this is how gang scheduling works. See, A0, A1, A2, A3, A4, A5, B0, B1, B2, B3, then B2, then C0, C1, C2, D0, D1, D2, D3, D4, E. Like wise time slotting is also done, and according to that CPUs are also divided so that they run at a time. All CPUs are scheduled synchronously. Time is partitioned into discrete quanta. That discrete means 0, 1, 2, 3 in similar variables. That is, if I take 2's divisibility, 2, 4, 6, 8, likewise. So quantum is like dividing the work into proper slots. At the start of each new quantum, all CPUs are rescheduled with new thread being started on each one. So new thread will be given to each and every gang when they start at the new. Also, at start of new quantum, another scheduling event happens. In between, no scheduling is done. So at every start, new quantum will occur. Another scheduling event happens. In between that, no scheduling is being done. If threads block, if any of the thread is blocked, its CPU stays idle until end of the quantum. So once they have the priority that they'll end up also together, even if any of the CPU is not working, it's blocked, it will set idle till it gets, the whole process gets ended up. Next is from here the second topic of this chapter starts, that is we had first topic as multiprocessors. This from here the topic starts multi-computers. So multi-computers means n number of, multiprocessors means n number of CPUs, multi-computers means n number of connections of your system together. So scaling multiprocessors with very large number of CPUs is difficult and impossible, and it is expensive also when we talk about multiprocessors. Solution on the same can be multi-computers, where each CPU has its own private memory. So each and every CPU, if they have their own private memory, this technology can be called as multi-computers. Multi-computers are also called as cluster of workstation, COW, that is cluster of workstations, because they have their own private memories. They do not work on shared memories. Only many PCs with high performance network interface card, NICs, The network interface card means NICs, is required to build multi-computers because they share over a network. Hence, it is not difficult to build. And as NICs can be transferred anywhere, it is not that difficult technology. So the first part here is interconnection topology. So when we are talking about the connectivity of multiple computers here, we require connectivity, and for that interconnection technology is being used. So for that, every node contains a network interface. So every node means, here you can see those boxes, single point boxes are called as nodes, and each of that node is connected to one area. So that node connects to a network, and that network interface card with one or two cables coming out of it means, if I have a Wi-Fi connection, I require a node to get connected to the satellite. So that is one node. If somebody else has it, another node. And for that, what do we require? We require cable connections. And these cables are connected either to other nodes or to switches, to the main switch or to the other nodes also it may be connected. Small system may have single switch. So small systems might have a single switching, but which all nodes are connected in star topology. So basically in star topology, you can say a single switch is being connected. The mesh or grid, modern switched Ethernets use this topology. Nodes are forming form of a ring. So first, that is the second one, this is called as a ring topology, and so on. I will tell you each and every topology. So the first one is a single switch, then second one is ring topology, third one is a grid topology, fourth one is, that is D1 is a double torus, E1 is a cube, and F1 is a A4D hypercube, that is interconnections internally, that is a 4-dimensional cube constructed for 3-dimensional cubes if with the equivalent nodes connected to each other. Then interconnection technology, when we are talking about switching, how it is done over CPUs, that is being shown. Switching schemes in multi-computers are of two types: store and forward packet switching and circuit switching. So store and forward packet switching is this one, and circuit switching and diagram is not being given here. In store forward packet switching, that is this one, what they are doing is, each message from application is first broken up into small chunks called packets. So every message will be divided into small chunks, that is pieces, which are called as packets. And in this scheme, packet is inserted into the first switch by the source node. So first switch, it is being sent as a source node, that is source data. And network interface board, when the entire packet arrives bit by bit, when the whole packet is being arrived at the receiver side, when the packet arrives at the switch connected to the destination node, the packet is copied to the node's network interface board. So then it is copied to the network interface board, and the packet and is finally to its RAM. So it's there in the actual RAM, that is random access memory. What happens in circuit switching? Circuit switching, first switch initially establishes a path through all the switches. So it directly communicates with all the switches first, and then reaches to the destination switch. After setting up a path, after setting a road for it, that is a path, the bits are transferred from the source to destination continuously as fast as possible. So circuit switching is a faster process. As once path is decided, it directly goes as fast as possible how it can reach the destination. Intermediate buffering at the intervening switches is not provided. So buffering processing is not provided in between to reach that destination. Setting up path takes some time. So setting up path like this path towards the destination takes a lot of time, but it's faster one. So it is faster than your actual store and forward packet switching. Setting up path takes some time, but it's faster one as path is set up. After the delivery of packet, the path must be toned down again. So after once the packet is being delivered, the path is being demolished, it's removed. Again when it has to transfer the data, it has to build the path again. Wormhole routing is a variation on circuit switching. So circuit switching has another what we say type, or we can say a variety, which is called as wormhole, WORMHOLE, wormhole routing, ROUTING, routing. In this scheme, a packet has been broken in sub packets. Now in wormhole routing, the packet is divided into sub packets and permits the first sub packet to initiate flowing even before the full path is being set up. So it does not here, even if it is somewhere a variant of circuit switching, but it does not set a path. Once the packet is ready, it will start sending the packet. It will not wait for the path to get completed. Network interfaces. Why do we require network interfaces? To communicate through network, we require an interface, and every node in multi-computer contain a plug-in board. So every node in the computer require a plug-in board with the nodes connection to the interconnection network that brings the multi-computers together. So for this interconnection technology, you require a proper connection switch to tie those multi-computers together, and for that, in the interface board, considerable RAM is present to store the outgoing and incoming packets. To store the outgoing and incoming packets, there is a RAM which is being present in each of the nodes, as you can see. Therefore, packets are first put in interface board. They are put in the interface board here, and then after that they are entered into the actual RAM. From the main RAM, continuous flow cannot be granted or guaranteed due to traffic on the memory bus. So we cannot assure that the continuous flow of data could be there. There could be discontinuity because of the memory bus which is being loaded because of multi-computer system. Incoming bits of packet also arrive from the network at a constant and often tremendously high rate. So these incoming packets also come very constantly and at a very high rate. Next is direct transfer from to network to main memory require access to PCI bus. This is the only connection it has to the main RAM. So there is a main connection to the RAM using a PCI bus. So competing for this bus with the disk is very and every other is very difficult, and every other IO device is expected. So every IO device expects that it should get that particular bus and is fighting for that. Therefore, incoming packets are first stored in the interface, board, and then they are sent back to the RAM afterwards. The interface board may contain one or more DMA channels. Now here interface board may contain one or more channel. The copy is block transfers of the system. And one more thing is, there is a CPU as well as one or more DMA, that is direct multiple access channel, or one or more CPUs. The DMA channels are used to copy packets between interface board and the main RAM at high speed. So there can be a connection at a very high speed using a interface board and your main RAM. Next is blocking versus non-blocking. How your blocking send call and non-blocking send call is. You can see the scenario how it is. Sender blocked, message being sent. Non-blocking here, sending running, message being sent, message copied to the kernel buffer. So these are the diagrams for blocking versus non-blocking calls. So choices on sending side, Blocking send, CPU idle during transmission. Non-blocking send with copy, CPU time wasted for extra copy. Non-blocking send with interrupt, copy on write. So these are the 4 conditions or calls which we can say when we define blocking versus non-blocking. Next is remote procedure call. So remote procedure, I might be giving you a description of blocking versus non-blocking with the diagram. I'll send you the image. Those who want can write from this image. Keep the answer ready for blocking versus non-blocking. As well as for remote procedure call also, I'll be giving you one notes type of pattern from the book which I refer with the diagram you have in the PDF, or sorry, in the video also. Next is remote procedure call. In remote procedure call, that is RPC's model, a client side process calls a procedure implemented on a remote machine. Remote machine means from wherever I can access with just one click is called as a remote machine. In this call, parameters are transparently sent to remote machine server where the procedure actually executed. So, transparently, the call will be sent to the remote machine server without any hesitation, procedurally to actually execute the task. The result of execution then the server send back to the caller. So, the server will send the reply to the caller that yes, I have got your response and request. While calling a remote procedure, the client program binds with a small library procedure called client stub. So they bind with one, as you can see here, they bind with one procedure call that is called as a client stub. Steps in making a remote procedure call, the stubs are shaded gray. So as you can see, both the stubs are shaded here as gray. Client stub stands for server procedure in the client's address space. In the same way, server program binds with the procedure called the server stub. So client's side it's client stub, server side it is server stub. So the diagram looks like this. What are the steps? Client calls the, so these are, as you can see, the numbers 1, 2, 3, 4 and 5. I'll read that steps. Client calls the client stub for connectivity. As client stub is on a client machine, this call is local procedure call, the LPC, and the parameters pushed onto the stack in the normal manner. So there are parameters are in the normal manner. Client stub packs the parameters into a message format and issue the system call to send the message. This process is called marshalling. So please keep this in mind. When second step, that is this one, when client stub packs the message with and sends it with the parameters and issues it to the system call, that is server, is called as marshalling. Kernel sends the message from the client machine to the server machine. Once this message is gone, that is 3, once these packets are being defined altogether and being sent, that time step 4, that is the kernel on server machine, that is this one, what it will do, send incoming packet to the server stub. It will send the packet to the server stub. And step 5, server stub calls the server procedure machine. So server procedure machine will be called by the server stub. As if you go with the arrows and numberings, you will understand the process. Still, I will be sending you this questions image so that it could be understandable and readable as well. With this, we'll stop here for this lecture. We'll continue with the next lecture tomorrow. Thank you.